Okay, 5 seconds. Okay, so I think we're on. I might have had some connection glitches. So good morning or good afternoon, everybody. This is the Stockholm time afternoon session. For me, it's the morning. In the joint AI and Music Creativity Conference. I'm Shlomo Dubnov, and I'm happy to chair the super interesting session. All of the papers focused on various applications of deep learning towards music creativity, computer-assisted music orchestration, other kind of karaoke, generating drum loops, and generating interactively with human in the loop for melody creation, and also auto tagging for loop-based music. So this is really a variety of aspects that we deal with when we have to create music, and we'll see how the deep neural networks can assist us in doing this. So our first speaker is Carmina Manuel Sela. I hope I pronounced the name right. And I will pass the microphone virtually to you. Please go on Slack for questions, and I will try kind of to moderate the questions and answers. And thank you.
Good morning to everybody. It's morning for me too. I am in California now at CNMAT, the Center for New Music and Audio Technologies of the University of California, Berkeley. This place has a long tradition in research for musical application, and the kind of expression machine creativity is always at the center of our work. So we have several topics in this moment, in the research agenda, and one of them is related to the talk that I'm giving today, that is about assisted composition techniques, or when the computers can help composers and musicians to make music, basically, in a very specific way. The specific subtopic that I will be focusing on today is so-called assisted orchestration. This topic is a long-standing problem for composers since several years. And IRCAM, the research institute in Paris, has been somehow the leader in the development of these research. And I've been at IRCAM for a number of years, and now I'm in Berkeley. So I'm working on this idea of using computers to help composers in orchestrating since a number of years now. So at CNMAT, we develop jointly with IRCAM and HOM, Haute École de Musique in Genève, a software called Orchidea, Orchestration IDEA, if you wish. That is somehow the state-of-the-art system for assisted orchestration. And so in this context, we have students working on some sort of evolutions of this approach or this problem. And this is the topic of this paper today. So let me open my slides so that I can actually share some information with you. Here we go. So this paper has been done in a context in which we bring undergraduate students in the research agenda at CNMAT, and they have a sort of internship for a number of months, and then the outcomes are oftentimes a paper or just a software, depending on the case. In this case, the 3 students are Luc Dvoncik, Alejandro Saldarriaga Fuertes, and Ongfu Liu, and have been supervised by me. My name is Carmine Accella. I am an assistant professor in music and technology here, and Hélène Camille Krahencourt, that is a researcher in Paris. So the idea of this work was, so since there is a state-of-the-art system called Orchidea that does orchestration, but this system only marginally uses neural networks for orchestration. So the idea was, can we think about a hand-to-hand system that could do orchestration completely, like giving files and getting the orchestration at the end. So this is somehow the beginning of this kind of research for us. And we have partial results at the moment, but I think it was interesting to see the potential of these technologies for the topic of assisted orchestration. So before describing the approach that we developed in this paper, I'd like to give an overview about the problem itself. So what is computer-assisted orchestration? Well, in a word, is sort of searching for combinations of orchestral instruments or sounds that match a target sound. So basically, you have a sound that can be whatever, like a recording, a bell toll, or a train, or a speaking voice, any kind of sound, physical recording of a sound. So you want to approximate this sound by putting together a number of samples from a database of orchestral instruments, so that when they play together, they sound similar or close, perceptually speaking, to the target sound. That's the kind of the general idea behind assisted orchestration. In other words, you want to reproduce a physical sound by using instruments, physical instruments. In the context of spectral music or spectralism, this idea is called usually instrumental synthesis. So we do synthesis using musical instruments. And as you can see here in this image, basically a solution to this problem is a score, right? So it's a score in which you select a number of instruments, a number of notes, dynamics, and playing styles. For example, here we see a clarinet playing an E4 in pianissimo, ordinario, and then a trumpet playing a B flat 5 in mezzo forte, staccato, and so on. So we have a number of samples that play together, should sound, let's say, as the target sound. Again, the outcome of assisted orchestration is not a sound, it's a score. So it's a symbolic outcome, right? But the input is physical, is a target sound. So is a recording or a raw samples, if you wish. So indeed, one interesting aspect of this software or of this problem in general is the fact that you go from the low level of sounds to the high level, somehow abstract level of score, like a symbolic level. This is an interesting problem, and this is actually a long-standing problem for composers. Today, given the extended techniques that composers use for music writing. When I say composers here, I specifically mean these kind of composers that work within the umbrella of contemporary classical music, right? So avant-garde music, if you wish. This is a bad expression, I don't like it, but in principle, this is just a way to say that this is embedded in the classical tradition. It's not like pop music or pop composers or jazz composers. It's more classical contemporary composers. In the recent years, I don't know, 50 years or so, instrumental techniques developed very much, and so the composers tried to add new ways to play instruments, And eventually, they ended up with a complexity that was kind of very difficult to handle by hand, right? So you would need some sort of computational support in order to drive your intuition and to help your imagination, because, you know, imagining together very different sounds made by very different playing styles and figure out the timbre would be very difficult. That's why these kind of tools developed. So let me review very quickly, which is the classic approach in solving this problem. The problem is made by a number of steps. Some of these steps use today neural networks, namely the optimization phase that you see on the right of this image. But the general idea is that you have a dynamic sound, like I don't know, a speaking voice, for example. Then you perform some sort of segmentation of this sound by any kind of novelty measure. So basically, you look for a new chunk of sound that is, you know, interesting for orchestration. Then per each segment, what you do is just you do an optimization. So actually, orchestration can be thought of as a combinatorial optimization problem. I'll explain why in a second. So this optimization that we have today is a two-step optimization in which we have a sort of pursuit strategy for pre-optimizing the situation, I would say the combinatorial space. And then we have an evolutionary approach for finding the solutions. When I say evolutionary, I mean that it takes inspiration from biology. So we have something that is very close to genetic algorithms. And this was one of the first solutions to this problem, and then is still one of the best solutions for the problem. And then, so this algorithm generates a number of solutions in time, and then there is a sort of connection algorithm that creates some sort of voicing or connection over time of this solution. We can think about that as sort of points in a graph, and you want to find a closed path in the graph, so to speak. Let me explain why this problem is actually a combinatorial problem. So suppose you have a single orchestra of two instruments. For example, you have a clarinet and a trumpet. And suppose that each instrument can play just two notes, okay? Then to find the best combinations of these instruments to match a target sound, you would just compute all the possible combinations, like one note of the clarinet, the other note of the trumpet, and then the second note of the clarinet, the second note of the trumpet, and so on. But this becomes very difficult to deal with if you have more notes, like we have, for example, 40 notes for the trumpet and 40 notes for the clarinet, on several different, dynamic levels. For example, pianissimo, piano, molto forte, forte, fortissimo, and eventually different playing styles, staccato, legato, and so on. And then what happens if you put into this game all the instruments in the orchestra, like all the strings or the winds or the brasses? So the combinations become too many. So you cannot actually compute them physically with brute force and then evaluate each combination to see how close this combination is with the target. So you need to find a heuristics that is able to actually navigate this combinatorial space in a smart way, if you wish. That's what we do with this double stepped algorithm, in which we have a pre-optimization phase using matching pursuit, a variant of matching pursuit, and then evolutionary optimization. So this was somehow this is somehow the state of the art of this solution. Now, of course, in these algorithm that you see, or I would say in this kind of workflow, we see a number of steps. And as I was mentioning, only one of these steps is done by neural networks. It is somehow the representational steps of the combination that happens in this box here during the optimization. So during the optimization, we use a neural network to compute the features of the combinations. And in fact, we don't compute the features, we just predict the features, because for some reasons we cannot really compute all the combinations. It would take too much time during the search. So we use a sort of forecast of the features using a neural network. But the idea behind the paper was, can we actually use a neural network to do all the job, to make a sort of end-to-end approach? Again, this was not meant to being the state of the art or doing better than the state of the art. It was just a first, trial, if you wish, to see what to which point we can go using neural networks. So the idea behind this method is very, very simple. So you have a target sound, as we had before, and then we train a neural network as a classifier. But what do we want to classify? So we want to classify at the same time the instrument that you find into this sound: the note and the dynamic level. So in other words, suppose that you train a classifier by inputting a sum of 3 sounds, like clarinet, E4, piano, and trumpet, B5, whatever, forte, and so on. So you have real instruments with real notes and labels, so you know which kind of symbolic elements you have in these sounds. Then you train the network to retrieve this information, okay? So this is the training phase. And then the idea of the testing is, instead of testing on a real combination of instruments like clarinet, piano, and flute, we inject into the network any kind of sounds, like, for example, a recording of a bell tone. And we want to see what the network predicts for this kind of sound. So the idea was, if we train correctly the network as a classifier, and the network is able to classify notes, instruments, and dynamics, then if we input a sound that is not made by these kind of components, the network nonetheless will predict these components for the target, for the input sound. So this is somehow how we go from classification to orchestration. The general idea is, I was saying, very simple. So we have a sort of probability function at the end of the network, and we use, so the peaks of these probability functions corresponds to the instrument. So we classify jointly the instrument and the note, and then we use the probability level to retrieve the dynamics of the sound. So if the sample is more probable, then probably it is more loud. That was the assumption at the beginning. So the outcome of this network is indeed a score, as it was in Orchidea. And we tested 2 major architecture for this classification problem. So we tested a sort of specifically designed network made by a convolutional network with an LSTM kernel in the middle. And then we used ResNet, so the residual network that has found excellent results for classification for images, for example. So we trained these 2 different models, and we ended up having nice results for classification. So these networks were able to classify correctly instruments and notes jointly, and using the probabilities for the dynamics. So we basically had so the first step of our research was to understand how good was the classification, and indeed we had quite good classification results. That was of course depending on the number of instruments. So if the combination of instruments was made by, for example, 2 instruments, well, the results were very good. But of course, if you went to up to 10 instruments, then the classification results dropped a little bit. But still, for example, with ResNet, we still had like 75% of accuracy in classifying 10 different instruments in the combination. So it was good enough for us to try for the classification. And so we made a number of experiments, and indeed the best results were always made by ResNet, but the CNN somehow did interesting results too. So we have a number of samples in online that you can actually check. So let me see if I can quickly switch to the other screen. I'd like to stop sharing my screen. Yes, here. So I think my time is finished, but let me just quickly go through this page here. So if you want to play these samples, there is this page here in which you have target sounds, like a bassoon, the solutions provided by Orchidea, and the solution by our system. And so you can play, I don't know, for example, this sound here. And then the solution generated by Orchidea. And the solution generated by the system. So to conclude, the system is not still complete, but it was first a trial, and we see promising results for the future. Thanks so much for your attention.
Okay. So I will pass some questions. Thank you so much for
Thank you.
wonderful presentation. My quick, maybe first thought, um, is this in some sense a continuation of the spectral music, Charles Griset motivation?
So yeah, in a sense, the cultural context is spectralism. So it is a tool that found its way within this context, this cultural context. So in a specific kind of music, which, for example, you use you take inspiration from sound analysis, right? So I think about pieces like Partiel by Griset, in which was using the sound of a trombone to generate spectra and to derive compositional parameters. This was done, by hand. Basically, you took the sound and you analyzed the parcels for the sound and the amplitudes, and you would derive some sort of compositional, information, like, for example, the notes or the dynamics. So automating this process would really help this kind of mindset. Like, if you work in this kind of music, then these tools could be very valuable. Nonetheless, I have so behind Orchidea there is a community of users, and there are very, very diverse profiles. So there are composers that don't really belong to this kind of music, and they use Orchidea nonetheless for other kind of purposes. So actually, to me, it was interesting to see how different could be the usages of your tools when you put these tools into the hands of artists, that they do very different things. So this tool has been used for example, soundtracks building. For example, you would record a natural soundscape and you would reorchestrate with your Orchidea, and so in that case, the outcome would not be the score, but would be the sound that Orchidea generates. Because, by the way, Orchidea not only generates the score, but it also generates the sound. So I think, yes, in short, spectralism is at the root of this project, but this project shows very different application nonetheless.
So we have one more related question by Gabriel Milinsoni. So he says, thank you for the presentation. Carmine, we have two-part questions. Don't you think the process implemented by Orchidea will also work in non-avant-garde musical context as well? And the second part of the question is, are there any specific characteristics in so-called avant-garde music that inform the design or condition the tasks in Orchidea?
Yeah, thanks for the question. It's really interesting. So I think to the first question I already answered. Of course, you can use this software in very different styles of music. There is nothing specific to avant-garde music in Orchidea. As I was saying, many other composers that, for example, do music for movies, they use Orchidea too. So it's totally depending on your needs, actually. And by the way, there is no connection to spectralism or avant-garde music in the system itself. So the system is, to some extent, agnostic to the style. The decisions are only made on timbre, basically. And so we can use these. So you should think about Orchidea as a system to approximate a given timbre using musical instruments. So as long as your problem fits these kind of definition, I think you can use Orchidea without problems. So there is nothing specifically related to style in Orchidea. There will be, because I'm working on a specific variant of this system, which we input style as a parameter of the orchestration. But the basic system, the system that will always be developed, is basically agnostic. So you can use it in any kind of musical style, if you wish.
So I think we have we have a little bit more time, a couple more questions. So Oded Vental is asking, what would be the advantage of using deep learning for these tasks that Orchidea cannot achieve?
The problem is that this approach has been developed during several years, and this kind of handcrafted approach proved to be very effective for orchestration. But nonetheless, there are problems that are very complicated. For example, and so we basically, the idea would be, let's see if we can use neural networks in some part of this project. So one would be to design an end-to-end network, but the other one would be to see if this end-to-end network would provide some useful representations, for example, for the task of assisted orchestration. Let me give you an example. When you start adding the idea of style, musical styling in orchestration, so instead of using just the timbre as the target of your orchestration, you would use timbre and style, suppose. then it means that the database or the data set would exponentially increase in size, because you need to add several elements that encode somehow the style, not only the timbre of your orchestration. And then methods that are not, so working with very large databases is an issue for many optimization methods. So this upscale, or this capability of going towards larger scales of the problems is intrinsic in neural networks. So I think neural networks could be a valuable technology to improve the optimization phase. That said, I'm not completely sold on neural networks today, so I'm researching, but I think that we should embed neural networks in a larger context that is always motivated by our knowledge or our needs. So this was an approach just to develop some tools, for example, to see how convolutional neural networks could actually represent sounds for assisted orchestration, and we learned something. But still, I think that the long is pretty long. The road is pretty long, sorry.
So I think we maybe have one more minute. Let me check if there's any other question. One technical clarification question, and but so you're matching spectral profiles, I guess. Are we sure that some phase information or spectral flux, I mean, are there other dimensions than the spectrum that maybe just are missing from the representation?
Absolutely, absolutely. That's a good question. Thank you. Absolutely. So this was a simplification again, because in the real algorithm that we have, the one that uses evolution optimization, we use we use time in a specific way. So segmentation is done using, for example, spectral flux. One of the ways to do that is using spectral flux. So we keep time into the loop of the optimization. This was not the case for neural networks, and so the optimization was done basically on either spectra or MFCCs, for example. And so you lose a lot of information. That's totally true. But it was kind of a first, attempt to see if, nonetheless, we could have something. And then the idea, so one of these students is Luke, will probably continue this work in this semester to try to add time back into this architecture and to see how we can shape a network in order to deal with time. And so that's why actually we started thinking about, LSTMs machines or memory-related machines to see what we can do with time and spectra.
Okay, thank you so much. I think we are 1 minute over time, so I guess whoever has more questions on the Slack channel, we'll be moving to the next talk.
Thank you.
We have a paper by thank you. Sorry, I kind of already moved on to present the next speakers. So the next paper is by Sophie Yuditskaya, Sophia Sun, and Derek Kwan. The title is Karaoke of Dream, a multimodal neural network generated music experience. I think the presenters here would be Sophia and Derek, right? We have both of you, so you'll be switching between the presentations. And for those on Slack, since we go by, I think, the first order, so the Slack will be under, I think, Yuditskaya. So please, I would like to welcome you, and please have the stage. Yeah.
Thank you, Professor Dobnov. Let me share my screen. Great. Present. Awesome. So we'll be talking about Karaoke Dreams. This is probably a more whimsical paper among the rest. There we go. We'll be first giving an introduction and showing a video demo, and then we'll talk about the neural network generated content creation part, and then the system implementing the generation and using it as an artwork. So Karaoke of Dreams is a site-specific art project that we made in one of our art residence at Bombay Beach, California. As you can see, it's located in the Californian desert. It has amazing sunsets. We have a site where Bombay Beach, California is a town that is semi-deserted but reinvigorated by artists in recent years, and there are a lot of crazy stuff going on in the town. Our project is sort of a homage to this town and the city and this community of artists, to say, yeah. This is our karaoke, the little box over here, among other art projects in one of our showcase nights earlier this year. So this is the context of Karaoke of Dreams. We wanted to use neural network to see if we can inject a little bit of techness in this vast land of nothingness. Derek.
Cool. So we three were together in this residency at Bombay Beach. It's called Brahman.ai. Now in the future, it's going to be known as Mars College, and it's led by machine learning. Machine learning artist extraordinaire, Gene Kogan. So like a bunch of artists and technologists were together in the middle of the desert, and of course we wanted to come up with like some projects to work on, and we came across the common ground of karaoke. And so why karaoke? It's like from the paper we cited by Mitsui and Hosokawa, it's a performance of intimacy, right? It's very communal. You're sharing like potentially embarrassing experiences with each other, and it's like a very bonding sort of thing. It's enabled by technology. Like, I guess you could do it without technology, like if you have like the lyrics and something to like play the music, but I guess like we all know it as like a video screen with like lyrics going across the screen and singing along. So us being artists and technologists, it seemed like a very natural thing to pick. And it's also a form of entertainment. It's like a time for us to like really let our guard down and like enjoy like each other's company, and like as like I'm a musician, and like Sophia is studying machine learning, so it's like a natural project that we could work on together, like joining machine learning and music.
Yeah, we're interested in it because it's one of the most prominent form of machine-human collaboration in some sense, and then it's done for a non-productive goal. It's an interesting form where we can perform cyborg art together in some sense. Yes. Okay. Let me share a video of the demo. So the system, how it presents to people is this is Sophie. Let me know if you can hear me.
I don't think you shared the audio.
Okay. This would be difficult, but let me show you the video first. So this is
So if you want to reshare the screen and share audio, there's the small button on the left when you share screen in Zoom. If you want to try that, I think it would be important.
Can you repeat?
Experience. Oh yeah, if you go back to the share screen.
Yes.
And when you click on this, you will have on the left a little checkbox that says share computer sound.
I don't think I see it. Yes, but it's okay. We can move on. The video link is on the paper, so feel free to. We have a demo. This is the system right here. The person sees an iPad, which gives them the lyrics, and then in the start of the demo, we have the interface, a screen recording of the interface, where they prompt the lyrics too, and then you can hear the music too. But yes, coming back to the camera. Yes, please.
So you just exited the share screen. So
Oh, dang! I'm so
Totally.
sorry.
No, it's fine. So if you go back, check again. I mean, you should see this small button on the left. Yeah. Okay. Yeah.
On the left. I
Oh,
don't
okay.
think
No,
I
before-
do.
Right.
Yeah.
Let's not.
Yeah.
Okay.
Yeah. Sorry. Thank you. So this
Okay,
is the interface where you see the lyrics coming on the top, and then when it's presented, it's mounted on like a smaller hypercube, as we say it, in the karaoke, and then the videos that are generated in the karaoke, in the sense, is projected onto the karaoke as atmospheric lighting and for people to view from the outside. So this is the feeling of it in some sense. You have the outside world, but you also have the inside world, and they're both visible to the viewer and to the singer at the same time. Cool. Sorry for the technical difficulties. Moving on to content generation. Great. So there are three parts in the karaoke in some sense: the lyrics, the music, the visuals, and we want all of them to be neurogenerated in some sense, because at Bombay Beach we only had one GPU and it's a shared resource with everybody, and we want to be, and it's powered by solar power, so we wanted it to be resource conscious. So instead of training models from scratch, we looked at downloadable on-the-shelf neural network trained models, and then we used it in a modular way so we can swap in and out models as if we want to improve in the future or have newer versions. The lyrics are very straightforward. It's a GPT-2 fine-tuned on pop song lyrics data sets available on the internet. Here is an example. We had members of the local community to give us song titles just as a primer of the on-site art. So the list of songs people choose from are a list of songs people demanded from us in some sense. And this is a quote from a local homeless person. And the song is in memory of him. He's an innocent man. Great. And the music generation is through a GAN-based music model called MuseGAN. It's trained on the Lock piano roll dataset, the Almighty. And then what it does is it's a convolutionary neural network that generates 4-bar piano rolls. This is a unfixed, uncleaned sort of example of what it's like. One of the bars in a 4-bar chunk. But as you can see, it has 5 tracks, and it was trained on pop songs. It has some of the pop qualities to it once you hear our demo. And then, so the chunks are mapped to the lyrics lines generated in the previous ones randomly. For visuals, the video projected onto the karaoke. We use the intention GAN, which takes in a caption and then tries to generate the image that fits the caption. As we can see, it's very abstract because a lot of our lyrics are abstract, but it has the dreamlike qualities that fits to the karaoke concept. And then after generating the images, we use a algorithm to have them transform from one to another. It's a video is generated for each song and projected onto the karaoke. Yeah. Now Derek talks about the system.
Cool. Awesome. Can we move next slide? Cool. So it's a picture of our installation in the desert and within Sophie Yuditskaya's Tesseract made by 2x4s. And basically it's an iPad as a user interface, a Raspberry Pi 3B Plus with the 4 speakers depicted as like the audio engine and the server, and a laptop with running VDMX, which is like a video performance software, and a projector for the visuals. And that was Sophie Yudiskaya generated, took care of the visuals. So we can move on to the next slide. Cool. So basically, the system software was a user interface, a web page using React, WebSocket communication with the server, which is Node.js web server, which is run on Raspberry Pi. It hosted a website for the iPad, which was the iPad connected to the Raspberry Pi via ad hoc Wi-Fi connection. Basically, the server's job was to load lyrics requested by the client line by line, and also communicate with the audio engine, which was Pure Data, which is this open source visual programming software specifically for audio. If you're familiar with Max, this is the same creator, but he later created open source version. It's called Pure Data. And so Pure Data was in charge of loading MIDI files, which was outputted, and soundifying it using synthesizers. And it's basically responsible for all timing information, deciding the tempo, telling when to load, to send lyric lines for Node.js. So if we can go to the next slide. Cool. So basically, the user interface, I tried to make it as simple as possible, so it didn't have to deal with logic at all. So it basically populated the list of songs. Like I had like an array of like the list of songs in React, and React basically took care of like all the dynamic aspects of the interface. So they had the song select screen as shown in that left picture, and the lyric display displayed in that right hand side picture. And basically it showed the lyrics one line at a time, as specified by Node. And since sometimes we had repeated lines, I changed the background color of that little box so I can tell when you had a new line. And if we can move on to the next slide. We had so basically this web page was hosted in Node. Basically, I used Express framework, and basically it communicated with the iPad via WebSockets, and PD via Open Sound Control, OSC. And basically the iPad, the user picks a song on the iPad, which sends like an index of the song, which is like all the songs have like there's like a common order between PD, Node, and the iPad. So I could just tell them apart by index. And so the iPad sent an index to Node, which in turn loaded the lyric file and told PD which MIDI file to load. And so PD basically tells Node to like send lyrics line by line via OSC. And as mentioned earlier, basically Node is handling all the logic between like switching between the different screens, because I wanted to make the iPad as simple as possible. So if we can move on to the next slide. Basically, PD loaded the audio, loaded the MIDI, it sonified it with synths, frequency modulation synths and drum synths, and basically took care of timing information. If we can move on to the next slide. Basically, when the PD loaded a file, it randomized a bunch of parameters, like parameters of the synths and the tempo. And basically the whole idea was to make each performance as unique as possible. So I can turn it over to Sophia now. She can conclude.
Yes, in the paper we talked to a bunch of people who have used our system, and the feedback was that because you and the machine need to collaborate, when the machine prompts you with music, you need to come up with the top line for the lyrics and the melody. It's an interesting experience similar to machine-human collaboration. And then you need to trust the machine. It fosters this, and you are in this atmospherically lighted box, which feels like the inside of the machine too. It has this estranged feeling, and that's sort of the vibe we're going for. Yeah. The full testimonies are also in our paper. They're fun to read. Yeah. And also there are a lot of things that we can do and can go forward with it. First of all, a lot have changed since March, I guess, in the machine learning space. GPT-3 is out, and then OpenAI has a very cool new model for music generation, which directly generates audio. It's called Jukebox. Magenta project also has a bunch of interesting models that we could use. So the music part can always be separated out. We're also thinking of having a web-hosted version of it, so the user can just input a song title, and then everything would be handled by the server. We can do karaoke of dreams via the internet. Yeah, and we're also thinking about other on-site constructions. What would it be like in a city? What would it be like in a town in different parts of the world? Also, our reviewers suggested we could do a more thorough UI UX study of the system and study the behavior of how trust works and how musical collaboration works between the user and the machine. And that concludes our presentation. Thank you.
Okay. Well, thank you so much, Derek and Sogyam. We didn't have right now questions on Slack. I'm sure that we can check this later again. For the sake of timekeeping, I think we'll kind of move on. I would just say that this was very impressive, and finding yourself in the desert with so much technology, it's almost like Elon Musk sending to Mars. But the images of the desert and the California sky with your installation, I think for me, just my personal impression was wonderful. Looking forward to check the sounds. Thank you. So our next speaker, Guillaume Alain, is going to present the paper on Deep Drummer, generating drum loops using deep learning and human in the loop. So Guillaume, please.
It says I can't start my video because the host has stopped it. Start my video. Can you see me?
I can see you, but
great.
And I can see your screen. Yeah.
Awesome.
Yeah.
We're set.
Yeah. All right. Sure.
Great. Hi, everyone. My name is Guillaume Alain, and I am going to be presenting our paper called Deep Drummer, Generating Drum Loops Using Deep Learning and Human in the Loop. So this is work by us four at MILA, the Quebec Institute of Learning Algorithms, aka Yoshua Bengio's lab. On the top row here, there's myself and my co-first author, Maxime. And in a way, we started this project with the intention of writing something that composes electronic music, but we ended up in a different place. And part of the inspiration for our project was some paper that I read 10 years ago. And I liked that paper a lot. It was based on the insight that it's usually easier to tell whether you like something than to actually guess what the parameters behind that thing are. And the example that they were giving was the example of a 3D engine in which some artist was trying to get the particular type of smoke or flame effects that they had in mind, but they just couldn't really say what the parameters for like air viscosity, gravity, number of particles, like what are those parameters that will get you the right kind of smoke effects. But if you see the smoke, you can tell this is what I want. And so they had this system that was doing active learning. So querying your user to make sure that to ask the user if what they're getting is what they want. And they were using Gaussian processes underneath. So what I liked about this is this dynamics of the system asking the user to rate something, because rating something is much easier than generating something. And so this, in a way, goes in a different direction than the popular paradigm about generating music as a sequence of tokens or events or notes. Like there's this very successful approach of treating music as an NLP problem, and you build a model that generates tokens. You learn on a big training set of sequences of tokens, and then you put a very powerful neural network on it, which is represented here by the dinosaur. And the idea is you have a lot of layers, a lot of neurons, large capacity, you train for a long time, and then you've got this powerful sequence modeling. So this is not what we're doing. And there's this GAN approach, which also involves two powerful pieces interacting. You've got the generator that tries to generate fake content that's meant to come from the training data set. And you've got the discriminator, which is also a big neural network, which has a lot of layers, a lot of capacity. You need to train it. Training it is hard. You've got this dynamics. They don't want to do the same thing. They fight, but at the end, you get a system that can generate samples that seem to come out of your training set if things work. But what we thought about doing was not that. So we thought about exploring a different idea. Like, what if we had something that we wanted to call a weak generator, for lack of a better word? So just a bunch of random patterns. And then what if we had infinite human patience and we were willing to sit there, and the weak generator would generate like a million samples, million loops or melodies or whatever it is. And then we painstakingly rate every one of those. And then at the end, we found like 10 things out of the million that sounds all right. Then we bring that to somebody else and say, voila, our system crafted those 10 jewels. Like, is that something that we really wanted to do? Like, no, but technically it sort of works, assuming they're willing to have infinite patience. So what if instead we could have a neural network that's being the critic? The neural network is going to try to learn what we like and what we don't like, and it's going to filter out like the vast majority of the garbage that comes out of the generator. Is going to be filtered by that. And then it's going to give us only the things that it thinks we will like. And so in a way, it tries to imitate us. It serves as a proxy for us. And what is special about this case is that, contrary to a situation where it would have to basically have ratings for all the search space, it's going to propose something that it thinks we will like, and we're going to say, no, we don't like this. And then it's going to go back to the drawing board and then try to generate something else that we will learn, something else that we will like. And so in a way, the labeling that's occurring is on the most relevant examples instead of garbage examples that it knows we don't like. So it doesn't have an incentive to spend time labeling the bad stuff. It only wants to label the good stuff, and it gets a lot of it wrong, but some of it right. So that's the idea that we wanted to try out. And for the sake of not being overly ambitious, like we started doing this with drum patterns, hence the idea of naming this Deep Drummer. So we are studying 16-step patterns of drums, which have four instruments. And by instruments, I mean like one-shot samples, so snares, kick drums, and all that. And in our setup, like, we did not want to label instruments specifically. So we picked about like 300 one-shot samples. We threw them all in a big bucket without saying this is a kick, this is a snare. and DeepDrummer just pulls from that and generates segments. And then it will try to learn our preferences for the generated content. And so it goes a bit like this. DeepDrummer says, hey, this drop loop X1 is something you like. And they say, yeah, we like it. Just add this to your training set. And it generates something else. Hey, this drum loop X2 is something you like. And we say, no, 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 this is bad. You remember that we don't like that, please. And then eventually, by training a lot more, it can be a good proxy for us, one would hope. Now, there's a difficulty right off the bat here. And this is why I was suspicious about this approach first. I thought that this wouldn't work because deep learning requires a lot of data. Like if our users rate like 80 drum loops each, say, that means that you get 80 bits to train a deep neural network. And that's stupid. Like deep learning is supposed to run on a lot of data. Even MNIST, like the most basic thing, has like 50,000 training examples. So is it really possible? But we implemented a prototype of it, and we definitely, my colleague and I both had the feeling that it was working. And this was the contradiction. Like it didn't seem like it was supposed to work, but it felt like it did. And so we wanted to investigate further. Like, and we thought maybe it's because of the active learning aspect of it that it works. We don't know, but it's worth an experiment. So the hypothesis is that if we do this interaction with a user starting from nothing, at the end of the interactivity, after 80 ratings, the drum loops generated are going to be better than they were at the beginning, and significantly better. And so how do we build an experiment to test this? And just as a reminder, the setup that we're using to generate those candidate drum loops is that we have this random patterns. We have one-shot samples, and we render that as an audio waveform. We feed that in a neural network, which has some MFCC features, convolutions, and then we output the predicted probability that the user will like that. And yeah, so the experimental protocol has to be split into two phases, and I'll explain a bit why we need to do that. So phase number one is where the active learning aspect is taking place. So we are going to ask questions to the user. Do you like this? Do you like that? And then after each response from the user, we're going to retrain our model. And then at the end, we think that we're going to have something better. Now, we can't just track what the percentage of drum loops being liked is, because then we might suffer from shifting user preferences. Like what if a user at the beginning has a tendency to dislike things more just because they're in a good mood, or I don't know, they're in a bad mood, and then at the end, for some reason, they feel tired, so they just start clicking like or dislike, and we remove the connection between the quality and the rating. So in order to fight this, we have a phase two. So we do phase one for 10 minutes. We have a short break, and then we do phase two. And in phase two, we're going to present them with drum loops, like new drum loops, either from the very first model or for the very last model. And it's going to ask for ratings. The user doesn't know if it's coming from the first model or from the last model. And then based on the ratios of drum loops that it likes, we're going to conclude whether the first model is better, no, the last model is better than the first model. And if it is, we're happy about it, because then it's no longer just a feeling, it's actually something measured. So because of COVID, we had to run this experiment online. We set up a web server. We issued a call to participation at Mila. At the end, we got 25 participants. So this does not include us. We got some more participants to be used to debug the prototype, but they're not part of that. And we wanted to keep the experiment short to avoid basically driving people insane, because what we realized was that after rating drum loops for 20 minutes, something weird happens to your brain and you start losing track of reality and what you like and what you don't like. So we wanted to be gentle to our users, and we wanted to find the sweet spot where we'd find some tangible benefit, but we weren't taxing the users too much. And I'm going to show you quickly just a short demo of what the interactions look like, and I'm going to go to the results after. So my colleague here is running through some ratings. So that's the first drum loop. She dislikes it. Click on dislike, please. Okay. Anyway, so that goes on for 80 ratings, and I'm going to show you now after, like close to the end, what it sounds like. So it sounds better than at the beginning. Also, she aggressively clicks like or dislike. You don't need to listen to the whole thing. But if you do want, the interface is going to play each drum loop 4 times and add 1 more second at the end for the sound to fade out. And oops, I'm going to show you some of the drum loops that I like. That was one I liked, and this one I saw. And we can ask the system to generate something bad also. Actually, that was a random bad occurrence, not a purposefully bad. Purposefully bad ones are even worse. Okay, so results now. So as I was saying, we are keeping track of what percentage of drum loops users have rated as good and as bad at the beginning and at the end. Now I'm talking about results in phase 2, where the users don't know which model the loops are coming from. So they couldn't cheat to favor the final model, even if they wanted to. And on the x-axis, you've got basically the percentage of times that they like things. And on the y-axis, it's the number of users in that bin. So initially, for the initial model, we've got a lot more people closer to 0. And for the final model, we've got more users closer to 1. So this suggests that there's an improvement. And funny enough, we've got 1 user out of 25 who liked nothing. They clicked dislike on every single thing. I think they had some expectation about what it was supposed to sound like, and they were let down. But hey, that's 1% out of 25. And I'm going to also talk about the deltas here, because like this is the per user difference. Is it getting better or is it getting worse? And the big mass of users is clearly in the positive. And so that means there's a bunch of people who liked things at the end, like 40% more. And by 40% more, I meant maybe at the beginning they like 20%, and at the end they like 60%. And there are some people who like things who are a bit disappointed at it, but most people have saw some improvement. And if we actually do the counts, we had 72% that saw some improvement, and we had 36% that saw an improvement bigger than 0.2. So that's nice. And just to be like more formal about it, we ran a Wilcoxon's test that confirms that the final ratios are bigger than the initial ratios, with a p-value of 0.00013. So we were happy about that. And we have our code online. We also have the drum loops that we generated during this experiment available, and we have a little demo on YouTube. Thanks again.
Okay. Thank you, Guillaume, so much, and all the others for fascinating paper and work. A couple of questions. So Bob Storm is asking, have you thought about asking participants to rate generated examples with respect to some well-defined characteristics, like 4 on the floor, instead of rate by whether you like it or not?
Well, we did try to enforce, I mean, just for fun, we did try to restrict the search space at some point to 4 on the floor. But the problem is it felt like the drum loops were more plausible, but they felt less inspired. It felt more mechanical, and And in a way, by not enforcing that constraint, we were happy when we found out that sometimes the drum loops that we generated ended up having on the floor kind of flavor, because that means that there's a rhythmic aspect that was learned. However, we did not ask the users specifically to watch out for a certain thing. We did ask in some exit survey if they felt that that the system had learned something, and we also had an open question asking them, so what did you generally use as a criterion? And this was just like, tell us a few words about how you made your pick, but we didn't really tell them what to look for. We weren't really sure what to tell them to look for, to be honest.
I see. And one more question by Gabriele Biglinsoni. I hope I pronounced the last name correctly. So Gabriel is asking, it's interesting you are combining rhythmic pattern generation and sound selection in one step. Do you think an easier task would be to split the task in two? That is, choosing specific drum patterns and then choosing specific sounds for those patterns?
Yes, we debated a lot about what the structure of this should be. And in a way, there's a lot of reasons behind the experiment that we ran that was about maintaining some kind of simplicity, in that at some point, because one of the things that you can do with such a system is you could technically seed it with music that you already like. Like you could dump like a gig in there of positive examples and say, I already like that. And then the system could learn from that, but from your input too. But then if you're running a system with 25 users, then how are you supposed to ask people to bring the music they like and dump this into there? So, but as for disentangling the rhythm and the sound, that could have been something else. Like that's a slightly different project. If we're asking like having a classifier about which sound our users like was something that we could have done, but we didn't do that. And at some point, one of the questions that we asked ourselves was, I mean, the biggest criticism about our paper that we formulated to ourselves, like we were thinking about that, is, are the users, I mean, is the system just learning what kind of sounds the users like? And then by producing drum loops with those sounds, users like them more. And this is what we're measuring. And the response to that is, there's definitely a rhythmic element to the sounds that come out at the end, which isn't there at the beginning. And so it can't just be the sounds. So it is doing both at the same time, but we are not really disentangling them. And this in a way is a bit of the like the deep learning approach of you do all the steps at the same time, and if good stuff comes out, you're happy about it. But yes, there's definitely something to be said about disentangling those two factors.
I see. So there is some interesting ongoing discussion about on the Slack about several people saying that they like the bad beats. So I'll try to summarize maybe the questions also for the sake of keeping the time.
Okay. I'm sorry. I'm okay. I am not seeing the Slack at the current time, so I don't know what's being said. Okay, but if you like the bad beats, then that just means that Deep Drummer is going to learn those quote unquote bad beats for you. Like the things I like don't really match what my colleague likes. Like sometimes I listen to the stuff that she clicked on and I said, I don't like that. And that's fine. And that's part of the experiment. And so it is going to go in the direction where you want it to. And if you're looking for something with like cowbells or novel ideas, or I don't know, maybe it will go there instead of doing some boring pop music, tried and true thing. I don't know. But if you like the bad stuff, it means it's not bad. It's just a different thing than what I was rating for, and that's fine.
Right. No, of course. I was kind of trying to summarize the questions of several people into one, but I think the sense that I understand from this question was really asking if the system is learning a preference or whether the user is getting tired in the groove.
Well,
in that sense.
We really try to learn a preference, but the thing about whether the user is getting tired, like if I'm understanding the question correctly, the reason why we had phase 2, and in phase 2 we sort of randomly showed samples from the first model and the last one, is because we decorrelate the fact that the user is getting tired with the ratings that they give. Now, I mean, there's still a way for the user to in a way start, like, if the user were tired and they really latched on a certain type of pattern and they clicked like for that and dislike for all the rest, then in a way it's a bit hard for us to disentangle. Do they like something because they're tired, or do they like something because they really like it? But what we certainly did is that in phase 2, they cannot, I mean, the ratings for things at the end are not correlated with the timing. So that means that we're not simply measuring that at the beginning they click like a lot, and at the end they click dislike more, or the opposite.
Mm-hmm. No, yeah, thank you for clarifying. I think the question was also considering the other way. Maybe the user gets adapted to the system, the user gets in the groove. So
yes.
Yeah, it can be both ways. He gets tired, or he gets excited, right?
Well, when you tried it first, I mean, my first experience doing this for the first time was a bit disorienting. Like, I thought, what am I rating for? And I clicked and I said, wait, do I like this? Do I no longer like this? And I felt like I needed to be coherent with myself and to rate the same things. And there is definitely some shift that happened in my mind the first time I did it. And then afterwards, after I did this for 10 times, because you can bet that we ran through this thing individually, each like 20 times to debug all the settings and all that. And at the end, like, I knew what I was looking for. And so the dynamics was a bit different. And we had to put ourselves in the mindset of the first time that we ran through this experiment. And yes, they might get into the groove, but then in phase 2, we're still going to compare patterns from the first model versus patterns from the last model. And if our users are in the groove, maybe they'll rate both a bit higher than they would have. But we're really looking for the delta between init and last. So if they both go up, the delta is still the same, hopefully.
Okay, so there are more questions running on Slack, but
so I'll jump on Slack then.
Yes, afterwards, I think, yeah. So I'm sorry to those who asked questions, and I didn't convey this now during the live interaction. But yeah, I would like to thank Guillaume for wonderful work and super interesting approach to using a powerful critic to train a not so powerful generator. I wonder if that says something about musical making in general, right? Maybe the musicians are not powerful and the critics are the ones who shape their yes. Okay, well, thank you so much. Our next presenter, and again, I apologize if I misspelled the name, so please correctly. Yujun Zhao, and it's a paper with also Yuki Koyamaya. Well, sorry, I will not read the whole list.
It's all the Japanese name. Yeah, okay.
Just because there are several authors, so please check all the authors on the paper.
I'll pronounce those names. Yeah.
Thank you. And the paper is generative melody composition with human in the loop Bayesian optimization. So, Eugene, please. Yeah, welcome you.
So I'll share my screen. Okay. I'm gonna present the paper. and Takeo Igarashi. So I'll start from our motivation. So humans are great at composing music for a long time. Well, nowadays, many research projects have tried to learn how to produce music, such as GAN, BAE. And when we sample the Latin vector on the smooth Latin space of those kind of generative models, even novice composers can quickly generate various meaningful melodies. However, novice users may face significant challenges when exploring the Latin space to find, I would say, a desired melody, since the Latin space is often unintuitive and high dimensional. So our motivation comes from it that we want to investigate how humans would steer the deep generative models to find their desired melodies. So in the following, I would like to introduce some related works in a short. And so I'll start from the tools. I will start from the Music BAE. It's a generative melody model, has a smooth Latin space, and we use this as our backend generative model. And we've seen many applications powered by the Music BAE and Magenta.js. Well, our systems shares a similar motivation to utilize the power of the deep generative model, but we focus on investigating the approach of formulating the task as a human-in-the-loop optimization. So for the next, I will introduce the Bayesian optimization and human-in-the-loop Bayesian optimization. Well, I'll call it a BO for the abbreviation. So BO is a black box global optimization algorithm. It finds the optima using a small number of samplings. It chooses the next sampling point by maximizing the expected improvement. I won't spend too much time on it. If you like it, please find the Shahiri's work. And I will introduce the human-in-the-loop BO. Well, it is an extension of the standard Bayesian optimization. It is designed for the human-in-the-loop sightings, and it can handle perceptual objective functions. And here is another image of this kind of process. BO iteratively suggests candidates to the user based on their preference. You can see that this works by the Koyama-san. And well, these projects are all using the human-in-the-loop Bayesian optimization. We share the same motivation, but our method is different because we iteratively ask the user to compare multiple melody candidates sampled from a one-dimensional subspace and select their preferred one. And yeah, so in the following, I will introduce our system design. So our system is a web-based application. The front end is implemented with the React kind of JavaScript, and the backend is managed by a Flask server. And all the music code data we process are on the MIDI level. And here is a demo video. Let me show it. Because from
I think you're not sharing the sound.
Okay. I'll try again. I checked the shared computer sound, and let's see whether it will work.
Each row represents a key on the piano from C3 to B5. The user can clicking and dragging on the note sheet.
Can you hear it? Sorry.
Yes.
Oh, okay.
Drag a note up and down to change its pitch. Click the play button. The user can play the notes to check whether they are satisfied with them. Right-click a note to delete it. The user can add 2 more blank bars by clicking the Add button. Delete them by clicking the Delete button. When they are hindered by lack of ideas, they can start searching. Choose 2 bars and open the searching interface. In the first iteration, candidates are randomly and uniformly sampled on the dimension-reduced latent space of the pre-trained generating model. The 2 bars the user selected are shown in the editing region. We suppose the user prefer the melody in the editing region to the candidates. The user can play a candidate to hear how it sounds. If the user likes a candidate, they can click it to select it. The user can always go back to the initial state of the current iteration, or go on the next iteration.
This kind of iteration goes on and on till the users find their favorite melody. And I will go on to go on with the algorithms and the implementations. So our implementation used the pre-trained music VAE melody for music generation. Well, its latent space is 512 dimension, and its main structure contained an encoder and a decoder. We use this to encode the MIDI level melody to latent space and decode the latent vector to MIDI. However, I would say 512 is too large for Bayesian optimization to work effectively, and we have to choose to dimension reduce it. So we tested several techniques for this purpose, including the principal component analysis, autoencoders, variational autoencoders, but we found that variational autoencoders of VAE work well in terms of minimizing the reconstruction errors and generate convincing and various melodies. So in this work, we use a smaller VAE, it's very small, to do the dimension reduction work. And another work called MIDI-Me also used this kind of techniques for the dimension reduction. And yeah, so for the training, we would say that 4 dimension is definitely not to encode, I mean, the original music VAE music data set. So we choose a small subset. We choose 10 songs covering the pop, rock, country, and R&B, and split them into 200, around 300 2-bar melody fragments to train this smaller model. And I'll show our problem formulation. So in the formula 1, function f represents the user's subjective preference over the melody, or how good the melody is. The would be the latent representation of the melody. The asterisk is the latent vector that generates the most satisfying melody to the user. And so the optimization target here is to find Z that maximize the F, function F, subjective function. And note, we do not know the landscape of F, which is the challenge of this problem. the goal here is to solve this optimization problem by iteratively presenting candidate solutions to the user and asking them to choose preferred ones. So you can see in the Formula 2, we will say on the left hand, after the editing, the melody X is preferred over those melodies on the right hand. I'll show the algorithm evaluation. We had a simulation experiment. We tried to simulate it, the user's behavior. So the goal is to verify whether our algorithm can find the desired melody in a reasonable number of iterations. We use the SDTW for the metric. It will calculate the similarity between two melodies. Well, the procedures are as follows. So first, we generated a desired melody by random sampling on the latent space. So when it's at the iteration T, it will give a set of candidate melodies. We will choose the melody with the smallest SDTW to the desired melody as the preferred one. And then it will generate another set of the melody for the next iteration. So we iterated this procedure for 50 times and performed 100 trials, and this is the result. You can find that the SDTW value decreased as the iterations went down, which was our expectation. And you can also see that in the latent space, the Euclidean distance between it is also decreased. I would say this means that it can be indicate the smoothness of the latent space. I would say the pre-trained music VAE latent space is smooth. I would say this would prove that our smaller VAE has a smooth latent space. And we also conducted a pilot study. We recruited 2 participants. They are novice. They never composed before. They had no formal composition training before. And they were asked to compose different tasks. The A is asked to compose a 32-bar melody. B is a 16-bar melody. A used 2.5 hours. B used 1.5 hours. And A used the search, that function to search the melody 8 times. B uses 6 times. And they have some comments. If I summarize it, I will say they expressed that the system had effectively provided them more ideas than they had, which inspired their creativity. I would say sometimes they did not use the generated melody directly. They found something good and they added it to their preferred one, I would say. And both participants also mentioned that the system made the process of the composition easier. Here's the result. I will only show the participant, the second one, because of the time limitation. If you like it, if you want to check, you can go to the website. There is a lag between the video and just the audio, but anyway. So right now we are waiting for the resources approved by the institute. So we will make this web application and the code publicly in this month. And let's come to the conclusion. our methods could work effectively and efficiently on searching for the user's desired melody from the latent melody space. And we also showed that Bayesian optimization could suggest satisfying candidates within a reasonable number of iterations. The pilot study result suggested that it also inspired the user's creativity and lowered the learning barriers of the novice composers. And for the future work, as also suggested by the reviewers, we would like to try to apply the Bayesian optimization to a higher dimensionality. We want to find a way to a higher dimensionality, like 512, effectively and efficiently in a, like in a kind of this kind of interactive system. And we also want to provide more control in terms of the searching behavior. Like we want maybe the user want to see something more, I would say, ambitious, or I would say more different from what they input or something like that. We want those kind of control for the users. Yeah, so yeah, thank you for the listening. So I think we can go to the question and answer round.
Yes, so Eugene, thank you so much for the fascinating presentation and the system description. So one of the questions on Slack by Odette Dontal was about the musical expertise of the two participants. Do you know? I mean, what was their musical expertise?
Yeah, we recruited these participants according to the criteria that they never composed music before, and also but the two participants learned musical instruments in at their earlier age, like around 8 or 6 or 8 for 1 year piano, and the other one is, I remember, is flute. So basically, I would say they have musical background better than those people without music instruments training, but they had no training or knowledge for the composition. They just, so we want to, because our target user is the novice composer. So, yeah.
I see. I have a question. When you show the table of how long they engaged, that was a couple of hours. I mean, this is the time it took them to select the melody, or these are multiple iterations? They worked 2 hours on one melody selection, or
the whole composition?
So I just wasn't sure when you mentioned that they. I think one of the users worked for 2.5 hours.
Yeah.
I don't remember exactly the slide. Was it the time it took them to compose one melody, or that is just their engagement with the system, so they composed multiple melodies during that time? I mean, how long it took them to select a melody?
Like search for one time, how long it would take?
Yes, per melody.
Yeah, we required them to, if they want to search, we require them to go at least 20 iterations.
I see.
Yeah, and then so it would took a lot of time, but from my memory, it would take 5 to 10 minutes, depending on the user, the participant, whether they want to edit the generated one. If they don't want to keep on clicking on the next iteration, it's much faster. But sometimes they got some ideas from it, and then they edit it. So that would be a little bit longer sometimes.
And do you plan to extend this to also polyphony or homophony, chords and melody? I mean...
Yes. We this is still a working. No, for this. I mean, for this process. I mean, for this stage, it is a complete research project, but it is ongoing project. We are implementing more control and more dynamics, and including the chord, because like right now we compress the octaves. I mean, the pitch note ranges into 3 octaves because we want to focusing on the main melody of a song or something. So we are trying to adding more the chord and even more instruments. So yeah, we are still working on it.
Okay.
Yeah.
But do you think this approach could work with, richer latent space? Yeah, it would be interesting. Yeah.
It will be interesting and will be a very hard work. So we'll see. Maybe we will find some methods to treat with this kind of thing. Yeah.
Okay. So I would like to thank our presenter.
Yeah, thank you.
And again, on the Slack channel, if you want to keep the discussion, please
Sure.
do. So we'll move on to our last presentation for this session. This is let me kind of quickly, yes. So John, you're with us. So the next paper is presented by Joan Qing, and I will let you also introduce the co-authors. And the title is Instrument Role Classification Auto-Tagging for Loop-Based Music. So please, Joan.
Okay, thank you, Professor Dubnov, for the introduction, and I will share my screen. Okay, so the project I'm going to present today is the loop role classification, which is about auto tagging for loop-based music. And thank you to Antonio and Dr. Yang for assisting me throughout this project. So in recent days, methods for assisting electronic music production have been emerging rapidly, and various creation interfaces such as Logic Pro, Ableton Live, Avid Pro Tools, and GarageBand and BandLab are all softwares that people can use to create music even at home. And especially the last two, which are free softwares, it's making music production even more accessible for people. So one specific style in electronic music production is to work with loops, which is one easy and engaging way. And since there are multiple public loops from the softwares, you get to create music even without the knowledge of music theory or any technical skills. And it's basically like playing with blocks. So you can just stack the ones that you like together. And for example, looking at the picture here, each block A, B, and C are representing different loops. So imagine this is a loop-based music that I just made. So what I can do is move the blocks around. Like say, if I'm not satisfied with this current version, I can probably take some A blocks out, or maybe take the last B block out, or say fill up the C blocks. And you can just move the blocks around until you've come to a satisfied version, and then you are done. So it's pretty easy and simple. And so as we are doing an auto tagging task, so auto tagging usually refers to automatically assigning semantic labels such as genre, mood, and instrument to music to facilitate text-based music retrieval. And besides genre, mood, and instrument, we present a way that's rarely been done before, which is to do auto tagging by an audio clips role. And why do we do it this way? Well, the point is, especially for electronic music making, we think that roles might be more useful than maybe the instrument that were used. So Therefore, having the tags of audio clips roll is an important information that can perhaps ease the searching process of finding compatible loops. So for those who are not familiar with what loops are audio excerpts, usually of short duration, that can be played repeatedly in a seamless manner. And compared to audio recordings of longer phrases, for example, pop music, or even longer phrases, classical music, the motive of a loop is relatively simple and straightforward, which the lengths are usually of between 1 to 4 bars. And therefore, we can summarize the loops within seconds. And here are some audio examples. Here is an example of a loop-based music. So let me choose. Okay. So what you're going to hear is at the first few seconds, you will hear 2 loops stacked together, and they will play the same thing over and over and over again. And then as time goes on, more and more loops will be stacked together. So you might know what I'm talking as soon as I play it. So.
I think it didn't share sound.
Is it not playing? Okay, sorry.
We cannot hear it, yeah.
Okay, wait. Oh, let me try it. Oops, sorry, too loud. Is it playing? Can you hear the sound now?
Yeah, we can hear it. Okay. Yes.
Okay. Oh, oops. Yeah, so hopefully you get what a loop-based music sounds like. Okay, so as we were saying, we do auto tagging by roles. Then what exactly are roles? And this might be the most confusing term in this task. So instruments don't always link to the same role. So you can think it this way. In a recording of, say, a band playing, like this picture over here, each track in the recording plays their own role. Like one may be playing the melodic part and the other one might be playing the percussive part. So what matters is the audio content, and it depends on what this instrument is doing in the audio. So for example, the synth pads over here, it can be linked to either effects or a melody, but you have to hear what the content in this loop is to determine whether it's a effect or a melody. So it can be played by a synthesizer, but what I mean is you have to listen to it to know the rules. So here are some examples for what it sounds like for each role. Okay. So the first one is pretty obvious, and it's a drum loop and it's linked to the percussion roll. So. And you can hear that it's basically repeating the same thing over and over again, which makes sense that it's a loop. And the next two, it might be a little bit, no. The next two are all played by synthesizers, but one is linked to effects and one is linked to melody. So they are played by the same instrument, but they are playing different roles here. Okay, and okay, so I hope you get what I'm trying to say here. And so in order to do this task, we build a prototype that's based on a convolutional neural network that uses a data-driven harmonic filter-based front end, which is called the HCNN, and it was derived from the work of data-driven harmonic filters for audio representation learning, which is cited down here. And so because of the harmonic filters, the model is able to capture local, spectral, and temporal relation. And in addition, the model is mentioned for its efficiency of learning. So for example, since our data set is so small, with only 2,936 loops, we expect the model to be able to catch important features for classifying. And now to show the effectiveness and accuracy, we used both neural network-based methods and non-neural network-based methods. For a neural network-based method, it is basically an ablative version of the HCNN, which uses the same network structure, but just without the harmonic filters. And for the non-neural network-based methods, the most common functions used for multi-label classification problems are binary relevance, label power set, and distinct random k-label sets. And we will refer to them as BR, LP, and RACL, respectively. So looking at the results, the accuracy difference between non-harmonic CNN and HCNN showed efficacy of using the harmonic filters. And also it's visible that due to the majority of loops being single labeled, the predicted answers appear to be trending towards giving only one label. So as you can see in figure C and figure D over here, they have multiple labels, but the predicted results, there's only one label being the peak. So yeah, and also another error case that might appear is for the voice loops, because voice loops is the least appeared label. So voice was categorized as either percussion or effects instead of itself. So, however, it is within a reasonable range because voice loops are usually either singing or beatboxing. So linking them to melody effects or percussion is still reasonable. And so for our future work, we might want to augment the amount of lesser appeared loops, like what was just said, the voice loops, for a more balanced data set. And we are also interested in using the loop role classifier as building block for automatic mashup or loop-based music creation. So perhaps a downstream application for a more referenced automatic mashup would probably be an interesting implementation. And thank you for your attention. And I guess we can go to the question and answer.
Yes. Okay. Thank you. Thank you so much, John. Let me quickly check what we have on the Slack channel. I think one of the questions that it seems that your work combines a lot of aspects, both of creating timbres by combining them together, right? So you need to know which functions each clip has with the annotation, but then each clip has its own temporal behavior. So it seems like you try to address very many different aspects of basically the composing of loops, which means what is your preference for the individual loop, like we had in the previous papers and questions about quality of melody or quality of a drum loop, and then you also try to put them all together. So it's like you asking questions about orchestration. So it's almost like your system has to answer all the questions that the previous papers were pointing to, right? Quality of the melody, quality of the drum loop, quality of the orchestral thing. Do you think the annotation itself captures all of these aspects in some way?
Well, actually, it's doing quite a good job of our targeted for our targets. Well, yeah, it's a probably a difficult task for machines to do this, but like in the loops, because different instruments are mixed together, and there might even be, there's probably multiple instruments in one loop. So, but basically in the data set, a single loop only has one, how do I say this? A single loop only has one targeted role. So there's usually no, well, at least I haven't ran into this, but I haven't heard like loops having both percussion and both, for example, both percussion and melody together. So yeah, it might be a complicated work for machines, but at least at this point, it seems like it's doing quite a good job.
Okay.
I'm not sure if I answered your question.
So, no, I mean, yeah, I think you did. I was just wondering if you had experience with people, using this system that it actually addresses all different aspects of music when they apply a method. But yeah.
Yeah.
But thank you so much.
I think one of the point for doing this task, for doing auto tagging in this way, is also to instead of a specific label or like a specific tag, we're kind of like pulling it back a little bit. So like the target range is a little bit wider, but I think it's musically a little bit more reasonable. Like it's not so specific, either it's wrong or it's right, but there's a range of reasonable answers. So yeah.
Okay, well, thank you. This is very interesting work, and definitely has a lot of practical applications for DAOs, as you indicated.
Yeah.
All right, so I don't have any. I don't see any other questions. I hope I'm not missing anything. So I would like to thank all our presenters for the fascinating session, and of course thank our host, Bob Sturm. I think we're kind of right on time. If anybody would like to join the session together or have a few last words, or Bob would like to summarize something, please do. If not, then I would like to, again, thank everybody and the audience, and hope to see you in, actually tomorrow. I think it's the last session for today, right? If I'm not mistaken.
We have the keynote tonight.
Right, okay, yeah.
Alice Eldridge. So that'll start in 4 hours. But thank you, everybody, and thank you, Clevo.
Mm-hmm.
Take care, stay safe.